In this chapter, we will be learning about logarithms. In this lesson, we will be looking at the laws of logarithms. And we will start by looking at the product law and the quotient law.
Okay, so the first two laws that we're going to look at here are going to be the product law and the quotient law. And you should recognize what we're about to do from previous lessons here, because we're covering very, very familiar ground here. So the log base A of the product of two factors here, okay, is equal to the log base A of m plus the log base A of n. In other words, logarithms here, when there's a product within a logarithm, that's the same as the sum of the two separate logarithms here. Now, and the reason why that's true here is, let's say that you had, for example, a to the x times a to the y, okay? When you have the power, a product of two powers here, okay, well, when you multiply those together, what is the overall exponent? Well, the overall exponent is going to be the sum of the two individual exponents. This is that same law. Because remember, a logarithm is an exponent, okay? A logarithm is an exponent, so the overall exponent is going to be the sum of the individual exponents. Same thing here. If we've got the log base A of the quotient, okay, of these two terms here, then that's going to equal the log base A of m minus the log base A of n. And again, that's because if you've got a to the x divided by a to the y, okay, the overall exponent on that expression is going to be a to the x minus y. You subtract. When you're dividing powers, you subtract exponents. When you're dividing, because remember, what a logarithm does is it's producing the exponent. So the quotient of those powers is going to be the difference of those individual exponents. The exponent, at least, I should say. Anyway, those are the rules here. Okay, so logarithm takes multiplication, converts it to addition, takes division, converts it into subtraction. That's actually one of the reasons why logarithms were developed in the first place, to help astronomers when they're doing arithmetic with really, really large numbers, because it's easier to add than it is to multiply. Now let's put that to some good use.
Simplify and evaluate the following. The log base 2 of 12 minus the log base 2 of 3.
Okay, so in this case right here, that subtraction between the two logarithms is going to become division. So this is going to be equivalent to 12 divided by 3. Now we know that 12 divided by 3 is just 4, and the log base 2 of 4 is going to be 2, because 2 squared is equal to 4. And so there we go. Log base 2 of 12 minus the log base 2 of 3 is equal to 2.
The log base 6 of 9 plus the log base 6 of 8 minus the log base 6 of 2.
Okay, now the important thing to do when you're working with a problem that's written like this is to go left to right. Okay, so the log law that we just looked at here is going to take this addition and convert it into multiplication. So we're going to have this log, so this is going to equal the log base 6 of 9. That addition is going to become multiplication, so 9 times 8. And then that subtraction there is going to become division. So we're going to divide it by 2. So 9 times 8 divided by 2, all within this log base 6. So this now becomes the log base 6. Now, 9 times 8 is going to be 72, divided by 2 is 36. Okay, and then the log base 6 of 36 is just 2, because 6 squared is 36. So log base 6 of 9 plus the log base 6 of 8 minus the log base 6 of 2 is just 2.
The log base 5 of 10 plus the log base 5 of 75 minus the log base 5 of 2 plus the log base 5 of 3.
Okay, now to do this one here, it makes sense that the first thing we would do is simplify what's inside the parentheses here, okay? So this is going to equal, now inside that parentheses there, we've got the log base 5, it's addition, so there's going to be the product of those two here. So log base 5 of 2 times 3, or 6. We're subtracting that. Now out here though, I mean, granted maybe looks like I'm doing this in order here, left, right, first, but I can do this at the same time here. Log base 5 of 10 plus the log base 5 of 75 is simply going to be the log base 5 of 750. Okay? Now, at this point here, that subtraction right there, okay, is going to become subtraction. So it's going to become the log base 5 of 750 divided by 6. Okay, well, 750 divided by 6, what do we got here? It's going to be 125. So this is going to be the log base 5 of 125. Okay, good. And the log base 5 of 125 is 3 because 5 cubed is 125. So that expression up there, now I'd read that off here, but for right now, I mean, you can see that that whole expression right there is going to be equivalent to just 3.
The log base 2 of 2 plus the log base 2 of 3 minus the log base 2 of 6 minus the log base 2 of 8.
Okay, so I want to walk you through this one. This is an important example here because of what it illustrates. There's a little rule that I'm going to give you guys in a little bit. Okay, not right away here, but I'll hint at it with this one. I might even just give it to you at the end here, but let's talk about this one first. Remember that according to BEDMAS, order of operations, when you've got a string of addition and addition subtraction here, essentially what we do is we do it left to right. Okay, that still applies here. We're going to go left to right on this problem here. I see a lot of people make a mistake here because when they see the subtraction here, they know that it becomes division, but they end up kind of going backwards. For example, what they do is they ignore this negative right here and go, that's log base 2 of 6 divided by 8, and then they put this subtraction in there and try to make it division again here. But that's not at all the way that works. Okay, you're going the wrong way with this. So let me just take this bit by bit here. So this is going to become the log base 2. This is going to become multiplication. So 2 times 3. Then we divide by 6. So it becomes 2 times 3 divided by 6. And then I divide by 8. Now where does that go? Let's just talk about this over here. So I've got 2 times 3 over 6. Over 6. Now I'll erase this and clean this up in just a second here. What's inside the logarithm is going to be 2 times 3 divided by 6 divided by 8. Well, when I divide by 8, now think about that. That's like 8 over 1. Dividing by 8 over 1 is the same as multiplying by 1 over 8. So just like the dividing by the 6 put the 6 in the denominator, this additional dividing by 8 puts it in the denominator. Okay, so what I'm left with here is this log base 2 of 2 times 3 divided by 6 times 8. Now, the 2 times 3, okay, that's going to become 6, which will cancel with the 6 there. So this becomes the log base 2 of 1 over 8. Which is going to become, well, think about it. What exponent do I got to put on 2 to make it look like 1 over 8? Well, first of all, because it's 1 over, I know that the exponent's got to be negative. Because it's 8 that's equal to, this has to be 2 cubed. So there's my answer here. Okay. Now, another way of thinking about this is you can simply put all of this into one logarithm really, really quickly. Any term here that's positive, its argument ends up in the numerator. Any term that's negative, its argument ends up in the denominator when you put those all together. That's always the way that works. So you don't have to go through step by step here. You can just clump them all together really, really quickly. Works quite nicely. And this hints at a little rule that I'm going to give you in a bit here, but there's just one more law of logarithms that you need before this little rule that I have makes sense.
The log base 2 of x plus the log base 2 of 2x minus the log base 2 of x squared minus the log base 2 of y.
So in the previous question I was talking about where you put terms here when you're combining these logarithms. So this is going to equal log base 2. Now here we go. I'm just going to run through this instead of kind of going step by step by step here. Just notice that the first two terms are positive, so that means I'm going to have x, 2x in the numerator. The second two terms here are both negative, so I'm going to put x squared and y in the denominator. Don't even have to think about it. That's where they go. Okay, and now this is going to equal the log base 2 of, and now I can simplify a little bit here. I've got x times x over x squared. Okay, so the x's all cancel, and I've got, the log base 2 of 2 over y. Okay, that looks as simple as I'm going to get it at this point here. Now there's some other stuff that I might do to this, like you might even look at this and say, well, I can break that up into, if you wanted, okay, just as an aside here. Okay, that just as an aside. You could make that log base 2 of 2 over y. Because that's division right there, you could make this the log base 2 of 2 minus the log base 2 of y. And then that just becomes 1. The log base 2 of 2 becomes 1 minus the log base 2 of y. Now, whether that's simpler or not, it's kind of up to you, but it's something you could do. This is very likely all that they wanted you to do at this point.
The log base 2 of 8 times 4.
All right, here's a good example of what makes logarithms so much easier to work with here than just straight out multiplication here. I could multiply 8 by 4 to get 32 and then figure out the log base 2 of 32, but then I got to know my powers of 2. Or I could just do this. I could take that multiplication, I could convert that into addition. Well, see, I like that. The numbers I'm working with are a lot smaller. I already know that the log base 2 of 8 is 3 because 2 cubed is equal to 8. And I know that the log base 2 of 4 is going to be 2 because 2 squared equals 4. Oh, and then 3 plus 2, 5. Okay, so right there, and I know, and I mean I do know that 5 to the 5th is equal to 32, the product of 8 and 4 here. So that all worked out really, really nicely here. This is just a nice little use of logarithms, to get around a multiplication problem.
5 raised to the exponent log base 6 of 9 plus the log base 6 of 4.
All right. Kind of like this problem just the way it sets up here because I know that's going to work out quite nicely. In the exponent there, I've got 2 logarithms being added together, and so I know that that means multiplication. So log base 6, and this is going to be 9 times 4, okay, or 36. I know that the log base 6 of 36 is going to be 2 because 6 squared is 36. And then finally, I can write down that 5 squared is equal to 25. I like that question. I like the progression of thought in that question. That would be a good like quiz or exam sort of question.
A to the exponent log base a of 8 plus the log base a of 2.
Okay, similar to the previous one here, I've got these 2 logarithms in the exponent here, so I'm going to put those together. Again, addition between the logarithms is going to become multiplication within, so this is going to become log base a of, well, 8 times 2 is 16. Okay, so a to the log base a of 16. Well, and I know from a previous lesson here that when you've got a power base a to a log base a, those are inverses of each other. They cancel each other out, and that'll equal 16, whatever the argument of the logarithm is. Worked out really nicely. Like it.
And now we'll spend a few moments looking at the power law.
All right. Now, here's the third law of logarithms here, the power law. And what this is saying here is if you've got log base a of m to the power of n, okay, m to the exponent n, I should say, that we can rewrite that by bringing that exponent down out front and multiplying it through, okay? Now, the reason why this works here is because if you've got a, let's say to the x, all to the power of y, to the exponent y, so a to the x, this power to that exponent, how do you evaluate that? Okay, how do you take that power to that exponent here? Well, what you do is you multiply the exponents together. Now remember, the logarithm is the exponent. So what this is saying is that the exponent of that overall expression is just the product of the exponent that we took it to, okay, and the exponent related to that power, just the product of those two. So you can multiply it down. It's the same rule, okay? The power of a power is just the product of the two exponents. Now, please remember though, and this is a big note at the end here, and I'm very glad this is in here, that if you've got the log base a of m times n to the r, you cannot bring the r down because the r is not the exponent on n. If you took that r back up, if you were to take that rule in reverse, this here would be equal to the log base a of, in brackets, mn to the r. Okay, so that the r applies to both those, the factors in the argument of the logarithm. Here, though, the r only applies to that one factor, the n. And so these two are not equal to each other, and that's something that they're going to test you on, okay? And you got to be really careful with this. If you're going to split this thing up, the first thing you got to do is take that multiplication in there and make it addition, okay? And then you can bring down, then you can bring down that r. Log base a of n. Got to split that thing up first and then bring the exponent down. That's the only way to do that.
Evaluate the following without a calculator. The log base 4 of 16 to the 12.
All right, well, the trick to evaluating these things without the use of a calculator is to do your best to make sure that you're working with the smallest numbers possible. So take a look at this. I've got the log base 4 of 16 to the 12. Okay, well, 16 to the 12 is going to be astronomical, okay? It's going to be large. Well, I'm saying that. I don't know exactly how big it is, but it's going to be big. Now, I can make this smaller because I can bring that 12 down. It's an exponent on a power in a logarithm, so I can make this equal to 12 times the log base 4 of 16. Now the numbers that I'm working with are actually quite a bit more reasonable. Log base 4 of 16 is going to be 2 because 4 squared is 16, and then 12 times 2 is just 24. See, and that, when you break it down like that, that's actually quite easy to work with. But if I try to do 16 to the 12 first and then do the log base 4 of that, couldn't do it.
The common log of 10 to the 21.
All right, now this one here should be really straightforward if you're paying attention. Notice that the base of the logarithm isn't shown, which means it's a common log, which again means it's base 10. So what I've got here is log base 10 of 10 to some power here. Now remember, there is a rule here. If we had log base a of a to the n, the answer here was n. Well, this means that this is going to be equal to 21. 21. Now, if you're not entirely comfortable with that, well, there is another way to think about this. Or you can see it like this. This is going to be equal to 12, or sorry, not 12, 21. My mistake. Because I've got a power inside the logarithm as an argument, I can bring the exponent down. So 21 common log of 10. But the common log of 10 is just 1. So again, that will just go to 21. Kind of either way you think about it, you're still going to get 21 as a result.
3 times the common log of x minus the common log of x cubed.
Okay, I like this question because I watch students kind of flounder with it. And it's not like I enjoy watching them flounder, but when they kind of see what's going on here, it's like, ugh. This question is really just about keeping your eyes open. I got one of two things I can do here. I can either bring that 3 up or I can bring that 3 down. It really doesn't matter how you go about doing this here. If you decide that you're going to bring the 3 up and then you're going to combine them because of the subtraction here, that 3 becomes the exponent on the x. And so this becomes x cubed minus common log, okay, if the base isn't written, it's common log, okay, x cubed. Now, subtraction becomes division, so this becomes the common log of x cubed divided by x cubed. But x cubed over x cubed is just 1, and the log of 1 is just 0. Or you could have noticed right here that log of the log base 10, the common log of x cubed minus the common log of x cubed is just equal to 0. Now, if you're still not seeing why that's true, it's because you're looking for some sort of logarithm law. Look, if I told you a minus a, and sorry, if I said a minus a and say, what is it equal to? Oh, well, the answer is 0. These two are exactly the same when I'm subtracting them. And the answer is 0, kind of regardless of how you approach that.
1/2 multiplied by the log base 2 of 16 minus 1/3 times the log base 2 of 8.
Okay, now as I said earlier, one of the things we want to do here to help us evaluate these is to try to make these numbers as small as possible. Okay, now maybe I don't know what the log base 2 of 16 is, maybe I don't know what the log base 2 of 8 is. I know that if I can bring the half up, right, so this is going to become the log base 2 of 16 to the 1/2 minus the log base 2 of 8 to the 1/3. Now, 16 to the 1/2 makes that number smaller. The square root of 16 is 4. Whoops, sorry, this becomes... And by the way, this is not the only way to go about this problem. It really isn't. I mean, you do know, if you've done some work with this already, you know what the log base 2 of 16 is. It's going to be 4. And you can take half of that. But I'm trying to give you an example of what you can do with these problems if they do get a little bit bigger. Take that exponent up because I know the exponent's going to make this number smaller. This becomes the log base 2 of 4. Okay, whoops. And I know what that is. Over here, this becomes the log base 2 of, well, the cube root of 8 is 2. So now I can evaluate those. Those numbers are small enough that I'm quite comfortable with it. Log base 2 of 4 is going to be 2 because 2 squared is 4. The log base 2 of 2 is just 1 because 2 to the 1 is 2. And then finally, you got to love this, 2 minus 1, 1. And there's your answer. Not the only way to do that, but if those numbers get kind of bigger and a little bit more ornery, then again, this is a good way of thinking to get yourself through that problem.
2 times the common log of 5 plus 2 times the common log of 2.
Now, in this question here, this is kind of an exception to that little rule that I've been giving you, but I think you'll see what's going on here in a second. Normally, I want to make these numbers as small as possible because they're easier to work with and they're smaller. But the base isn't written here, so it's base 10. I don't know what log base 10 of 5 is. I also don't know what the log base 10 of 2 is. So that doesn't work here. So what I now want to do is kind of go backwards with this and see if I can help myself out here. So I'm going to bring that 2 up and make this the common log of 5 squared plus the common log of 2 squared. Now, and this is going to equal the common log of 25 plus the common log of 4. And at this point, I'm starting to see where this is going here. Addition is going to become multiplication between the two, within the arguments there. So this will become the common log of 25 times 4, or 100. And now I know that the common log of 100 is just going to be 2, because 10 squared is equal to 100. So in this particular case here, making the numbers as small as possible or leaving them there just didn't help me because I didn't know what to do with them. But I can go backwards with that, and I made that a little bit bigger, and it did work. Most of the time, though, you're going to see in a lot of these questions, what you want to do is make those numbers as small as possible.
Write each of the following as a single logarithm. The common log of b plus the common log of d minus 5 times the common log of e minus 5 times the common log of a squared plus 1/2 the common log of a.
All right, now with this question, I'm going to introduce you to my little rule that I use to help people answer questions like this, and really to help them solve logarithmic equations when we get to it. And the rule is this, quite simply, 2 steps, 1 log. Okay, whoops, 2 steps, 1 log. You should be able to get an expression like this down to 1 logarithm in 2 steps. I've already kind of hinted at what one of those steps should be, I should say. But now that we've gone through the power rule, okay, the other step is available for us to use here. So when I take a look at a string of terms like this, all with the logarithm in it, and I'm supposed to put them together, the first thing I'm going to do is move up the coefficients into exponents. Okay, so I'm going to move that 5 up, I'm going to move this 1/2 up, so this is going to become the common log of b plus the common log of d. Now this will become minus the common log of e to the 5th minus the common log of a squared, and then this is going to become plus the common log of a to the 1/2. Okay, now all I've done is moved up those coefficients. Now I'm going to put them all together into 1 logarithm. So here's my second step. I'm going to read this thing left to right, okay, and I'm just going to obey what the little signs are telling me. So I've got a positive log b here. That means when I put those together, the b is going to be in the numerator. Plus, okay, addition I should say becomes multiplication, so b times d. Subtraction becomes division, so e to the 5th goes in the denominator. Subtraction becomes division, so a squared goes into the denominator. Now remember what that means here. When I'm dividing by a squared, that's like multiplying by the reciprocal, which means it's going to go into the denominator there. And then plus, okay, log a to the 1/2. So I'm going to multiply by that, which means that's going to go into the numerator. Now, a lot of times where the confusion gets here is people look at this and say, well, wait a minute, but I'm multiplying this by a to the 1/2, and this is in the denominator. And my answer to that is, no, you're not. No, you're not. You're multiplying all of this by that a to the 1/2. The whole thing. You have to do this left to right. I have to do this before I can do the division. I have to do all of that before I can do this division. I have to do all of this before I deal with this addition here. So what that means is, because of the two subtractions here, by the time I get out to my log of a to the 1/2, I've already got a fraction going here. And when I multiply by this a to the 1/2, it's going to go into the numerator. So there it is. In 2 steps, I can get it down into 1 logarithm. And now my last step here is really just to clean this up a little bit. I got an a to the 1/2 in the numerator, a squared in the denominator. That's going to be a to the 3/2 down in the denominator when I simplify those exponents, right? So I subtract them and move that down. If you're not quite sure where that's coming from, again, it's just going to be, the exponent here is going to be 1/2 minus 2, okay, because division becomes subtraction in the exponent. That's going to be negative 3/2, which pushes it into the denominator. And there you go.
The log base 2 of x cubed minus 4 times the log base 2 of x minus the log base 2 of the square root of x.
So here's another one. Okay, we've got three terms here. Remember, 2 steps to 1 logarithm. So the first thing I'm going to do is get rid of that coefficient. And that was the only coefficient out of those 3. So this becomes the log base 2 of x cubed minus the log base 2 of x to the 4th minus the log base 2. Now this is the square root of x, but I'll write that as x to the 1/2 because that's going to be easier for me to manipulate here in just a couple seconds. My next step is to combine those into 1 logarithm. The first term here is positive, so that x cubed is going to go in the numerator. And then I'm going to put that x to the 4th in the denominator because of the negative, and I'm going to put the x to the 1/2 in that denominator because it's also negative there. So this becomes the log base 2 of x cubed over x to the 4th x squared, x to the 1/2. This is going to equal the log base 2 of, well, okay, x cubed over x to the 4th here. Okay, they're going to mostly cancel. I'll be left with an additional 1 extra factor of x in the denominator, and then multiplied by x to the 1/2 will be x to the 3/2 when you add those exponents. And so there's my expression, the log base 2 of 1 over x to the 3/2. I can play with that a little bit here, but that's really about as good as I need to take it right now.
4 times the log base 6 of y squared plus the log base 6 of y minus 2/3 the log base 6 of y.
Okay, and finally here out of this group, again, 2 steps, 1 log. So the first thing I'm going to do is bring up that 4. So log base 6 of y. Okay, this is going to be y squared to the 4, so y to the 8. Okay, there was a square there. I'm going to bring that up as an exponent. I'm going to multiply them together. There was no coefficient in this second term, so log base 6 of y. And then this last term becomes the log base 6 of y to the 2/3. Okay? Now, what I can do here is just put them together. I should say it like that. I can put this together in 1 logarithm. So the log base 6 of, remember, terms that are positive end up in the numerator, so this becomes y to the 8th times y, and then subtraction becomes division, so y to the 2/3. Whoops. And now I've got it as 1 logarithm. Now I can simplify. So this becomes the log base 6 of, okay, y to the 8th times y to the 1 is going to be y to the 9th. Okay, so y to the 9th, and then I'm going to divide that by y to the 2/3. So y to the 9th divided by y to the 2/3. So it's going to be 9 minus 2/3. So this will be y to the 25/3. Okay, the common denominator will be 3. 9 is going to be 27/3. So 27/3 minus 2/3 is 25/3. And that's the value that we're looking for. Now, before I leave this, I should note here, I could have done this a slightly different way here. I could have brought that 2 down and made this all log base 6 of y, log base 6 of y, log base 6 of y, and then combine the coefficients together and then move that up here. There is some freedom here. Same thing with the previous question, if I can go back here. I could have brought the 3 down, brought the 1/2 down. Again, there would have been a common log base 2 of x there, and I could have simplified the coefficients. It turns out I did the exact same work anyway, It's just a matter of what order you're doing it in. It's that previous question, I don't really have that opportunity, that freedom to do that, because in this previous question here, the variable changed at every step here. So I kind of was forced to do it in the way that I've been describing. Anyway, just wanted you to be aware that what I'm doing here isn't like strictly, rigidly got to be this way. There are other options here. But this will work for all of the questions that you're going to get.
Expand each of the following expressions using the laws of logarithms. The log base 4 of x cubed y over 4z.
All right, in this case, the 2 steps 1 log kind of works backwards here. So what we're going to do here is basically anything that shows up in the numerator, I'm going to split that apart with addition signs here. So this will become the log base 4 of x cubed plus the log base 4 of y. Now the two factors here in the denominator are going to become minus the log base 4 of 4, and I'll deal with that in just a second, and because that z's down there too, minus the log base 4 of z. All right, now, next thing I'm going to do is bring down the exponents, but I'm also going to evaluate things when I can here. But this has got an exponent, so I'll bring that down. So 3 log base 4 of x, there was nothing I could do here, so that stays the log base 4 of y, minus, but this one I can do something with, because the log base 4 of 4 is just 1. And then I've got this log base 4 of z, again, that I can't really do anything with because there's no exponent. And so that's what we mean when we want you to expand this thing out, as far as you can.
The log base 5 of the square root of xy cubed.
All right, now for this one right here, again, we're going to expand this thing out, and I'm going to go backwards with my 2 steps 1 log. But the first thing I got to do is deal with the fact that that square root, that is the same as an exponent on the whole thing. Okay, so I'm going to bring that down first. So this becomes 1/2 of the log base 5 of x times y cubed. Okay, so I got to deal with that, kind of that overwhelming factor there first, because it covers everything. Now what I can do is I can go into here and say, okay, now I've got multiplication between these two, and I can convert that into addition. However, that's true that the log base 5 of x times y cubed does split into addition here. However, that 1/2 is being multiplied by this whole thing right now. So what happens here when I split that up, I got to split that up within a set of parentheses so that both parts of it are still being multiplied by 1/2, just like they are out here. So this becomes the log base 5 of y cubed. Okay, so that 1/2 stays outside of this whole thing here. Now, the last thing I'm going to do is bring down the exponent. And so this is going to equal 1/2 the log base 5 of x, and then I got to bring the 3 down, so 3 log base 5 of y. And whoops, and now I've expanded that as much as I possibly can. Now, I could have done that a different way. We could have, for example, taken and distributed that 1/2 through. It wouldn't really have made a difference. All that would have happened is that I would have had these last two terms here with a common factor of 1/2 between the two of them.
The common log of 100 times the cube root of x to the 4th divided by y squared.
All right, one more time here, same as above. So again, in the numerator, we've got these two factors here multiplied together. So we're going to take our common log, apply it to the 100, and then we're going to add the common log. In this case, we're just going to take this cube root of x to the 4th. Now, that is the same as x to the 4/3. Right? That exponent there, sorry, this root index here becomes the denominator in the exponent. And then because I'm dividing by y squared, we're going to subtract the common log of y squared. Now, I'm going to bring down the exponents, but more than that, I know that the common log of 100 is going to be 2, because 10 squared is 100. Then I'll bring down the the exponents and make them coefficients, so this becomes 4/3 of the common log of x, and again bring down the exponent, so 2 times the common log of y. And that's what we're looking for in terms of expansion.
If the log base 3 of a is equal to t, then find the log base 3 of 27a cubed.
All right, now you might recognize this pattern of question. We've looked at it before, but we did it a little differently before. Previously, what we would have done is converted this logarithm right here to its exponential form and then done some substitution here. Now that we've seen the log laws, another way that we can look at this is we can take this log base 3 of 27a cubed. We can now expand this out the way we've just been doing with the last previous questions here. So this is 27 times a cubed. So I can make this the log base 3 of 27 plus the log base 3 of a cubed. Okay, now I know that 27 is 3 cubed. Okay, so this is going to be, this will be the same as the log base 3 of 3 cubed. And I can bring down that exponent and get the 3 times the log base 3 of a. Okay, now here's where we can start to do some substitution. First of all, I know that because this is 3 cubed, I know the log base 3 of 3 cubed is just going to be 3. But additionally, I know, based on the question here, that the log base 3 of a is equal to t. Now, I couldn't have done that here. I couldn't have made this t cubed right here because t isn't, okay, this right here, t is the log base 3 of a, okay? And here, this cube is only on a part of that expression. It's not the log base 3 of a cubed, all cubed. It's just the log base 3 of a cubed, okay? Just the a is being cubed here. It's just a portion of it. I need to get that out of the way here. Now I can make that substitution and make this 3t. And so here's our final answer here, 3 plus 3t.
Determine the value of 5 log base 5 of q minus 5 log base 5 of r if q is equal to 5r.
All right, now with this question, there's a few ways that you could approach it here. When I first take a look at this, for example, one of the first things I see is there's a common 5 to both of those. I'd be even tempted just to factor that out. So this becomes 5 times the log base 5 of q minus the log base 5 of r. Now we're told that q is the same as 5r, so I can make a direct substitution here and make this the log base 5 of 5r minus the log base 5 of r. Now from here, right now I can see something going on here because I've got this r and this logarithm, this r and this logarithm. There's a subtraction between the two, and I know that subtraction can become division. So this will become the log base 5 of 5r divided by r. All right, the r's will cancel, and I'm left with the log base 5 of 5, which experience tells me is just 1. And so the answer here is just going to be 5. 5 times 1 or 5.
If the log base a of b is equal to 7.3 and the log base a of c is equal to 5.1, determine the following. The log base a of b times c.
All right, well, once again, this question here is similar to one that I've done before here. In the past, what we did is we converted this into exponential form. So we would have made this b equals a to the 7.3, c equals a to the 5.1, and then done substitution here. But now that we've seen the log laws, there's actually another way that we can do this. What we can do is we can take this logarithm here and expand that. Okay, multiplication here becomes addition. And now I can make a direct substitution. I know that the log base a of b is 7.3. So here we go, log base a of b, 7.3. The question says log base a of c is equal to 5.1, so I just replace my log base a of c with 5.1. And when I add those together, I get 12.4. And so that's what the log base a of b times c would be equal to.
The log base a of b divided by c.
In this case, when we try to expand this thing out here, because of the division inside the logarithm, that is going to become subtraction. And so we'll get the log base a minus the log base a of c. So log base a of b minus the log base a of c. And then, again, because of the information that I'm given directly in the question, I can substitute 7.3 for the log base a of b and 5.1 for the log base a of c. And when you subtract that, we get 2.2. So this would be equivalent to the log base a of b divided by c.
The log base a of b squared.
Okay, now although I've already mentioned this before, this is another good spot to address this. This is not the same as 7.3 squared. Okay, please don't do that. that would be true. This would be true if this was equal to, in brackets, log base a of b squared, where the whole thing was being squared, because the whole thing is equal to 7.3. But when you write it like this, that's not true. It's only the b that's being squared, not the logarithm. So in order to make that the same, I got to bring that 2 out. And so this is actually equal to 2 times the log base a of b, but I know that the log base a of b is equal to 7.3, and so when you multiply that together, you get 14.6. So the log base a of b squared is 14.6.
If the log base 3 of 8 is equal to k, write an algebraic expression in terms of k for each of the following. Log base 3 of 8 to the 5th.
All right, so this question is very similar to ones that we've just done here. Once again, this is not equal to k to the 5th, because it's the 8 that I'm raising to the exponent 5 here, not the whole thing. So what I got to do is bring that down 5 times the log base 3 of 8. And now I have exactly what I need. The log base 3 of 8 is k, and so this expression here is equal to 5 times k.
The log base 3 of 64.
All right, now in this case here, to accomplish the same goal here, I got to look at this number here and realize that 64, although that's not the argument I want 8 here. That's easy enough to compare those two, because 64 is just 8 squared. And then, once again, I'm going to say it again, this is not equal to k squared, because it's the 8 being squared, not the log base 3 of 8 being squared. Okay, and the whole thing is equal to k here, not just the 8 here. So I got to bring down that 2. So 2 times log base 3 of 8. And now I can make that substitution. Log base 3 of 8 is k, and so the expression here is equal to 2k.
If the log base a of 5 is equal to x, and the log base a of 4 is equal to y, find an expression for each of the following. Log base a of 20.
Right, now I think the trick to doing these questions here is to think about expansion. Okay, and in particular here, the question gives me some direction to go here. I'm looking for log base a of 5, log base a of 4. So let's look at 20 here, log base a of 20. I know that I'm going to want to expand this, and when I think about my factors of 20, I see 4 and 5, or 5 and 4. And then I know, because of my laws of logarithms, that I can expand that multiplication within a logarithm becomes addition between logarithms. And now, based on the question, okay, and what it says here, I know that the log base a of 5 is x, and the log base a of 4 is equal to y. And so the log base a of 20 can be rewritten, according to their rules, as x plus y.
The log base a of 64 over 25.
Right. To answer this one, to kind of get into there and to tear these things apart, first thing I want to do is separate these two values here, 64 and 25. Now they're being divided. Okay, so there's some division here. So a logarithm changes that division into subtraction. So this will become the log base a of 64 minus the log base a of 25. Okay, now I'm looking for 4 and 5 in the arguments. 64 is 4 cubed. Okay, so 64 is a power of 4. 25 is 5 squared. It's a power of 5. Okay, now, remember what we've done before, and I tried to establish this a couple of times here. Although log base a of 4 is x, this does not become x cubed, because it's not the log base a of 4 being cubed here. It's just the 4 being cubed, just a part of that expression. So I have to bring that down. And the same thing over here. I got to bring down that 2. And now I can do the substitution. The log base a of 4 is y, so this becomes 3y. And the log base a of 5 is x. It becomes 2x. So we can say that according to their rules here, what they've given us, the log base a of 64 divided by 25 is equal to 3y minus 2x.
The log base a of 80.
Okay, this one right here, you have to be careful with this one, because you could tear this apart a few different ways here. What we're looking for, though, is, remember, going back up to here, we're looking for the log base a of 5 and the log base a of 4. Now, whoops, right away, I can see the 5 coming out of this, okay? This is going to be the log base a of 5 times 16. Okay, because now, again, because it's 80 here, because the last digit is a 0, I know that there's a factor of 5 in there, so I just yank that out first here. And then I can split that up as the log base a of 5 plus the log base a of 16. Now remember, I'm looking for 4 and 5 in here. Now 16 really quickly throws a little flag in the air and says, "Look at me, look at me, look at me," because 16 is 4 squared. Okay, good. Now, I want to bring down that exponent like I've done with all these other ones here. I'm going to bring down that exponent, make that 2 log base a of 4, and now I can make the substitution, the variable substitution in this problem. Log base a of 5 is going to be x, log base a of 4 is y. So the log base a of 80, according to their rules, is x plus 2y.
The log base a of the cube root of 100.
Now in this one right here, before I do much work with it, notice that this cube root is over top of the whole argument of the logarithm. So I'm going to deal with that right away here. I'm going to make this 100 to the 1/3. And then because of the law of logarithms, I can bring that down, make that 1/3 log base a of 100. Okay, good. Now I can focus on splitting that up because I've gotten rid of the exponent here. Now, 100 here is going to be the same as the log base 5, and I got to think about this. You can take out a 25 and a 4 here. So 25 times 4. And I'm going to split that multiplication up into an addition here, but bear in mind, this is 1/3 times the log of that product. So when I split that up, it's going to be 1/3 times the log, or the sum, I should say, of those two logs. I got to make sure I put parentheses around both of those because both of these together form that log base a of 100, and that 1/3 is being multiplied by that log base a of 100, both parts. Okay, now I know that 25 is going to be 5 squared. I don't really need to do anything with the log base a of 4. It's perfect, just the way it is. Let's bring down the exponent here, whoops, so that I'm dealing with just exactly the expression that I want to work with here. That's the log base a of 5. Okay, so this is going to be 1/3. Log base a of 5 is x, so 1/3 of 2x plus y. So there we go. 1/3 of 2x plus y is going to be equal to, okay, the log base a of the cube root of 100.